Welcome back to my Devlog series. Alright, let's get the most important thing out of the way. With a dash of black magic and a few days digging through the engine code mines, I got rotation sweeping to work. Now the nature of reusing code for something it wasn't intended to do does bring the performance into question, but we'll cross that bridge when we get there. Anyway, I have managed to make some decent progress on implementing my custom motion solution. If you need a refresher, you can check out my previous video, linked below. Since many of you said you like more technical content, I'll do a deep dive, or, well, maybe a deep-ish dive into how I've implemented the system so far. I doubt anyone would really watch a 3-hour video discussing the intricate technical details, so I will try to keep this somewhat short and focused on the more interesting parts. Some of the motion components I've implemented so far are sliders, levers, or levers, axles, and springs. Definitely the thing that took the most effort to get done was all the 3D math around constraining movements and converting hits to new movements. I also spent a bit of time researching and developing custom debug tools for each component to help visualize the results. I want to take a moment to shout out stevestreeting.com for a really nice guide on how to draw extra stuff in a neat and modular way such that it only affects editor builds. There's also a Git repo that has tons of helpful code for Unreal developers, so check it out. The best place to start breaking down what I've done is probably with what I call the Motion Manager component. This is an actor component that will need to be added to any actor that makes use of a motion component. From the user perspective, it's fairly simple to use right now. On startup, it finds and catalogs all the motion components in the actor. Then the user can call one of two functions, add relative location or add relative rotation, which will kick off the motion solving algorithm. Otherwise, there are some callbacks the user might want to handle, like on component seized, which is mainly just for triggering the primer on the round right now. The motion solving function, creatively titled solve motion, takes a motion object which contains the component, the amount to move, and a completion percentage. First, we take this instigating motion and put it on the motion stack for processing. Then we do a sweep for this motion, more on that later, and check if we got stuck or not. If we didn't hit anything and finish the motion, we pop the current motion off the stack and exit since there's nothing else to do. Maybe that was a little too easy. Let's run through a more complex scenario. We put a motion on the stack, we sweep it, and now let's assume we got stuck because we hit something. In that case, we'll tell the motion solver attached to the thing we hit where the hit came from and ask it if it wants to do anything about that. Assuming it does, we record how far we got into the current motion and push the new motion onto the stack. This process basically continues on forever until we finish the original motion or our PC lights on fire. We can go up and down the stack as much as necessary. In the case that we can't finish our motion, we call the onComponentSeized callback I mentioned earlier to indicate that the moving part smashed into something that can't move. Okay, let's talk about how sweep motion works. We get all child components and make them part of the sweep too. Then, because Unreal Engine doesn't natively support rotational sweeps, we have to split the logic to handle rotations in a special way. Before we go any further, I'd like to point out that these algorithms are sort of reentrant because I keep around the completion percentage. This way I can do some part of the requested motion, get interrupted, and do motion for other things, and then come back and finish the first motion, starting right where we left off. Okay, translations work like this. First, reduce the remaining delta according to what the motion solvers say, which could go all the way down to 0, in which case we're already done. Otherwise, sweep from the start location to the end location, and this will find any hit along the way and return how much free space we have. For reasons I'll get into later, we then do a callback saying we're about to move, and then really do the move according to how much free space we have. Actually, we'll use a slightly smaller delta to help prevent overlapping parts. Finally, we update our completion percentage for the next time around. Rotations are very similar, except we sweep many times at small rotation increments, and do a very small translation just above what the engine considers too small to be a legitimate sweep. We keep sweeping until we find a hit or reach 100% of the requested motion. Okay, so how are motions made? Well, there are currently only two types of motions: relative translations, or linear motions, and relative rotations. Some motion components only produce one type of motion, others produce both, or maybe even none. Let's start with how slides work. As the name suggests, the part will be restricted to sliding back and forth over some distance, meaning the hit response will always be a translation. Looking at the debug tool for this part with a slide attached to it, we can choose any line or vector along which to constrain the part. We can also adjust the overall length with the direction of the vector going from the red sphere to the green sphere. Notice how the vector needs to be at least as long as the distance from the start to the origin of the part, and if the length is longer than that distance, the vector always passes through the part's origin as well. This shows that the part's origin is what is being constrained, which means this point inside the part is what is bound to the red and green spheres. Moving on to levers, we'll see how the hit response will always produce rotational motions. The debug tool looks like a rectangle with a line coming straight out of the middle. To put it technically, this shows a YZ plane centered at the pivot point of the part with the normal of the plane aligned with the part's x-axis. What that means is, when we look from the side, if the debug plane rotates, this line will show us how far around the part's y-axis the plane is being rotated. Now, this may start to get complicated, but bear with me. Here we can see what it looks like when I constrain the part's range of rotation. The green line shows the limit of how far the part is allowed to rotate in the positive direction. The red line shows how far the part is allowed to rotate in the negative direction. And when we look from the side, we see those lines together will show us the arc of rotation that this part is allowed to do. Okay, got it? Good, because we're just getting started. Let's see what happens when we simulate something hitting the lever. If I perfectly align the hit marker with a pivot point, you can see, especially when looking from the side, that there is no change. This makes sense, right? If you push the exact middle of a seesaw, it won't move. You need to push on one side. So let's do that by grabbing the debug hit location marker, and we'll see that we're always drawing this plane between the pivot point and the hit marker. Now I could move this anywhere, but the only thing that makes sense to do with it is to put it on the surface of the part. Because we can only get hit when something actually touches us, right? Okay, we can see we're pretending we got a hit right on the surface there, and it's coming in from the direction of the yellow line. Here's where things start to get interesting. So whatever is hitting us looks like it wants to push us downward, right? But this fake hit isn't actually trying to push us anywhere yet. It's just perfectly resting on the surface. Now let's set it to push us 1 centimeter forward. Notice that as I increase the hit depth, we can see that the point on the green plane the blue line touches is changing. This shows us that the distance the exact hit location on the surface will move is highly variable. The green color of the plane and the delta line shows we will need to create a positive rotation motion. You can also see that eventually the rotational boundary is reached and larger hit depths will be ignored. Of course, this also works in the negative direction, and we can see that hit angles that are closer to the pivot point will result in much more extreme motions even if the hit depth barely changes, with hit angles further away from the pivot point not changing much even with large hit depth changes. Finally, even though I've been keeping the hits constrained to the XZ plane for these examples, you can see here the results are still correct for hits from arbitrary directions. You can probably guess that this is where I spent most of my time since the last video. I can't even express in human words how much I despise quaternions. Let's move on to springs. I don't have a debug view for these, as I'm mostly using them to return parts to their default positions. Maybe if I can figure out how to draw a debug mesh, I can do something here, but like I said, it hasn't really felt necessary yet. The main thing springs are for is to generate either a translation or a rotation based on a selectable target location or orientation. Overall, they were extremely simple to implement, however they are taking a lot more effort to fully stabilize. This is because as long as the part isn't at the desired target, it creates a new motion every tick and slows down the game a lot when all the extra debug code is enabled, which makes the game hard to interact with. Also, when a spring is constantly forcing parts into each other, it seems to have a high chance of creating these tiny overlaps, which end up confusing the collision detection. I'm still trying to figure out how to clean that issue up nicely. And finally, axles, which are a bit different from the other parts in that they don't generate motions on their own. What they actually do is pass through hits to the part they're attached to. This might be a little hard to understand, but essentially what we want to happen is when we push on a part that isn't allowed to move, we take that same force and move it to the location where the child is attached to the parent. Then ask the parent if it would do any motion for our fake hit. In a sense, the axle sort of extends the collision volume of the trigger to include whatever is on the other side of the axle. But that's not all they do either. In short, they do a little cheating for now. The reason I called it an axle is because I allow it to counteract rotations of the parent as if the child is free to rotate around the location where the parts are joined together. This explains why, even though the hammer catch has no other motion solvers tied to it, it is able to translate back and forth when the trigger rotates. I think I'm going to redo this later, as I'm not able to do this counter rotation inside the motion manager. If I did, the hammer catch would hit other parts first and stop the trigger from moving correctly. Okay, so we saw how individual components work, now let's see how it all works together. First, I use the mouse to create rotation motions for the trigger. The axle cheats and perfectly counter rotates the hammer catch at the same time, which makes it look like the hammer catch is only moving backwards. Then, a spring in the hammer rotates it forward, while another spring starts to reset the trigger. Eventually, the hammer pushes the firing pin forward. Since each one has a spring driving them, you might see them fight a little bit. Once the firing pin hits the round, the bullet will be fired, the internal ballistics are calculated, and then recoil pushes the bolt back. Side note, right now this happens in a single frame instead of over time. This causes the bolt to reset the hammer. Then the bolt spring starts pushing the bolt forward again, while the firing pin spring also resets itself, and the hammer catch catches the hammer until finally we're back where we started. Since I like devlogs that aren't only about fluffing up the dev in the game, let's have a section on some of the issues I'm working on as well. And as always, feel free to share any ideas about how to resolve these things. I mentioned this before, but right now, if the part is not at the target location, the spring will constantly collide against whatever is in the way. My current hack for this, so I can focus on other functionality first, is to simply disable the spring if it hits something it can't move. So I think maybe some algorithm that slowly backs off springs by slowing down their tick rate and eventually putting them to sleep might help. The last problem I want to discuss here is the thing I've been banging my head against the wall on for a while, which is how sometimes the hammer halts the bolt even though both are moving forward. I'm not quite sure why yet, as it looks like the hammer actually hits the firing pin and somehow that stops the bolt from moving. I suspect it's due to some sort of tiny overlap, but it's tough to pinpoint because it doesn't happen every time either. I think it might be cool to show the uncertainties of development as well, instead of pretending I have all the answers all the time. So here's a bunch of open questions I have about the project. My simple motion system is much more predictable and controllable than a full physics sim, but can I make it fully deterministic? Should I even try to make it deterministic? If it's not deterministic, what kind of restrictions will I need to put on shapes, distances, and usable rotations in the full game to ensure a design is consistent? How many logic parts will I need to cover really difficult edge cases? One example of a logic part might be something like the primer in a round. We can't just explode a round because it was pushed forward, we need a hit at a very specific location. But I don't want to create a separate object when the primer isn't even something that would ever move. So it would be nice for the round to have a non-physical or logical primer added to it that simply checks if hits are close enough to make it go off. How many other logic parts will I need though? If there are consistency issues, would players rather have extra logic nodes to fix them or more intuitive but restrictive designs? This kind of feels like cheating, but I'm one guy with a dream and a lot left to do. Let me know in the comments if you'd prefer complex designs that rely on logic, or designs with restricted complexity that are consistent and intuitive to build. How long can I avoid tracking physical aspects of movement like force and velocity? Would I actually be better off adding movements as physical impulses and letting the motion manager be its own mini pseudo-physics engine? Right now, you could sort of look at it like every part has infinite mass and infinite force, so you don't have to sit there and tune the mass of the bolt to make sure it's enough to overpower the bolt spring and push the hammer back at the same time, but not so massive that it can't be pushed back by recoil either. I think that sort of tuning isn't the main source of fun and should be implemented in a limited capacity. I can see it getting really easy to cross the line into a full-on simulation game rather than a simulacrum game. But tell me what you think in the comments. Is that something you really want to do? Or do you agree the appeal of the game is more about making cool Rube Goldberg style contraptions instead? And finally, let's talk about the priority of next steps. First, I'd like to integrate player part manipulation with the new simple motion system. Currently, the code is set up for the old way that directly changed the mesh's transform. Instead, I need it to convert those changes into motions and pass them to the motion manager. It might even be worth it to finally convert all that into C++ while I'm there. Next, I don't really like that the bolt moves all the way back in a single frame, so I need to figure out how to apply the force from the gas block correctly over time. And I'm actually cheating right now since the bolt isn't being moved directly by the piston. It should be driven by the piston hitting the bolt block, which in turn throws the bolt backwards. Once that's out of the way, I can start looking at ejecting the round, and then after that, how to make the bolt feed a new round from the magazine, which of course means I'll need a whole system for supporting magazines. Finally, maybe, it would be getting the bolt to lock and unlock correctly, after which, I think that would be all the critical parts for simulating the Johnson. Since I keep getting repeat questions in the Discord, I figured I might as well clarify some points here too. While not all the weapons I show at the beginning of these videos will be in the game as they appear, I'm choosing examples of the kinds of things the game will allow players to create, or recreate, as close as I can reasonably support on my budget. So yes, there will be sci-fi weapons too, and no, it's not all going to be revolvers and World War II relics that I'm making by hand. The game will be about designing what you want, and then putting those designs to use in fun scenarios and missions. Oh, and since I'm apparently supposed to farm for engagement, how about the first person to correctly comment what series this is from will get a free emoji? No purchase necessary, void where prohibited. This was a lot more detail than I usually go into in these videos, so let me know in the comments if you like this style, or you just rather see shorter updates, or whatever.